Hello everyone and welcome back to physics class. Today we are going to be talking about projectile motion. So projectile motion is when you have an object that is being thrown in two dimensions. And when I mean two dimensions, I mean that it's being thrown horizontally and it's being thrown up. So it will have some kind of arc looking like this, where we have the horizontal component, and then we have the vertical component. Now, projectile motion is not just confined to this particular example where we have it at an angle like this. It could also be if you have something falling off a table, for instance. So it could look like this, which is like half, essentially, of this trajectory. So here you can see that we have the horizontal, and then we have the vertical right there as well. So projectile motion basically combines the two types of motions we've talked about so far. Uniform rectilinear motion, which is the constant motion that we see. So constant motion meaning that there's constant velocity. And this happens in the x-axis along the horizontal. Now we also have the accelerated motion part. And this is where we have changing velocity, right? We have acceleration happening. And this happens along the y-axis. So when we analyze projectile motion problems, we actually have to break this up into the two components. Otherwise, we can't really solve these kinds of problems. It is important to note that both these components, the uniform rectilinear motion on the x-axis and the accelerated motion on the y-axis, are completely independent of each other. Now, one thing to note about our uniform rectilinear motion, there is no acceleration. So acceleration is equal to 0. Then when we want to talk about accelerated motion, we need to consider that this is in free fall. So these are the important things that we have to remember. Along the x-axis, we have no acceleration. Along the y-axis, we consider free fall. Therefore, our acceleration is equal to negative 9.81 meters per second squared. So when we look at projectile motion, there are equations for the horizontal portion of the motion, and there are equations for the vertical portion of the motion. The equations for the horizontal portion are relatively simple because, remember, this is going to be our constant velocity portion. The first one that we need to remember is that the velocity is constant across the entire thing. So that means that your final velocity along the x is going to be equal to your initial velocity on your x. The next formula involves displacement and time. So we've isolated our displacement along the x, so delta x is equal to our initial velocity on the x times delta t. Now when it comes to vertical motion, we have a couple of formulas that we will use, and these ones are based on accelerated motion. So the first one is our final velocity in the y is equal to the initial velocity in the y plus your acceleration times time. Now it's important to note that the time for both horizontal and vertical motion is the same. The time is the same, so you can use the same time for both of these types of motion. The second formula is delta y. So this is our displacement in the y direction, and we're specifying it with the y here, is equal to your velocity in the y plus your initial velocity in the y times delta t divided by 2. The third one is delta y is equal to v naught y delta t plus a delta t squared divided by 2. And then the last one is v y squared is equal to v naught y squared plus 2a delta y. So when we consider projectile motion, we are looking at these different formulas here. Let's go ahead and take a look at an example. All right, so here we have a ball being thrown horizontally off a roof that is 50 meters high with a velocity of 5 meters per second. How far from the building will the ball be when it touches the ground? So I'm going to just draw a little picture right here. So this is our building, this is our ball, and we're throwing it horizontally. When you throw it horizontally, your trajectory is going to look something like this. We know that the height of the building is 50 meters. We know that the velocity is 5 meters per second. And we want to know how far away it lands. This is going to be a multi-step problem. Let's write down all of the information that we know. V, because it's horizontal, it's just Vx. So we know that V initial in the x is 5 meters per second. We know that the height of the building is 50 meters, and when a ball is falling, that means that it travels in the negative direction. So our delta y is negative 50 meters. We also know that our acceleration is negative 9.81 meters per second squared. And because this is horizontally launched, our initial velocity in the y, so v naught y, is going to be equal to 0. All of the velocity was put towards the horizontal motion, so there was no velocity that we started with in the y direction. So this is the information that we know. Now, we are looking for delta x. But in order to find delta x, if we look at this formula, we need to find what our delta t is. Let's figure out our time first. So if I take a look at my formulas here, which one would I want to use? Well, I don't know what my final velocity is in the y direction, so I can't use this one, and I can't use this one. This means that I would want to use this one right here. So delta y is equal to v naught y delta t plus a delta t squared divided by 2. Since v naught y is 0, I can just cross that out and say it goes to 0. Then my negative 50 goes here, is equal to negative 9.81 delta t squared divided by 2. This becomes negative 4.91 delta t squared, and then I divide both sides by negative 4.91. This way I get 10.2 is equal to delta t squared, and to get rid of the square, I square root both sides. So then I find my delta t is equal to 3.2 seconds. I know that my time that I found, 3.2 seconds. So that was the first step. Next step is we're going to use this formula here to find what our delta x is. So delta x is equal to v naught x, which is 5, times our time, which is 3.2 seconds. When we multiply that together, we get a total delta x of 16 meters. And there is my answer. So this example states that a soccer player kicks the ball with a velocity of 20 meters per second at 25 degrees above the horizontal. We want to know what is the total flight time of the ball. So let's just draw a little picture to help us understand. So we have our ball here, and we know that it's being kicked upward at an angle, and we know that it's going to go wee through the air like this. So let's start labeling and figuring out the information that we have. We know that the initial velocity, v naught, is 20 meters per second, and we know that it's at an angle, right? An angle of 25 degrees. Now, before we go any further, notice how this velocity combines the horizontal and the vertical motion. In order for us to solve this problem, we need to take this and make it into its different components. So we have to use vector components to do this. So I'm going to do this really quickly right now. V naught x would be equal to V naught cosine theta, which in this case is 20 cosine 25, which will give me 18.1 meters per second. Same thing with the y, except this time I'm using sine. So 20 sine of 25 will give me a vertical initial velocity of 8.45 meters per second. Let's rewrite what we have. We know that we have v naught x is 18.1 meters per second. We don't know how far it goes. We don't know the time, so that's basically all the information that we have for our horizontal motion. So I will just put delta x is equal to question mark, and then delta t is what we're looking for, so I'll put that after. Now we're going to look at the v naught y is 8.45 meters per second. We know that acceleration is negative 9.81 meters per second squared. We don't know what our delta y is, and we certainly don't know what delta t is. Delta t is what we're looking for here. So we have a little bit of sleuthing that we have to do. So we know that when the ball reaches the top of its trajectory right here, it changes direction. Now, when it changes direction, we know that the velocity is equal to 0 up there, right? So what we're going to be doing is we're actually going to be looking at how much time it takes to get to the top of its trajectory. And then, because it takes the same amount of time to go up as it does to come down, we can find the total flight time. So I'm going to be putting down, I'll put it up here, v y is equal to 0. If we look at our formulas here, we can see that we can use this formula right here. So Vy is equal to V naught y plus 8 delta t. This is 0. This is 8.45 plus negative 9.81 times delta t. We bring this guy over, it becomes negative 8.45 is equal to negative 9.81 times delta t. Divide both sides by the negative 9.81, and we get delta t is equal to 0.86 seconds. So this is the time it takes for the ball to reach halfway. Now to find the total time, we're just going to take this and multiply it by 2. So total time is 0.86 times 2, which gives us a total time of 1.72 seconds. Thank you for listening, and I will see you guys next time. Bye!